Voice over Internet Protocol, or IP telephony, uses the IP network to send voice data in packets. In this course, we begin with an overview of Voice over IP and video conferencing, including TCP/IP, DHCP, real-time protocols, and Skinny. So that you can better troubleshoot your VoIP calls, I'll review network operations, quality of service, DNS, and directory integration. We'll then take a deep dive into Wireshark statistics, including graphs, service response time, PDU boundaries, and VoIP calls. Wireshark Voice over IP is an intermediate course for network administrators, students, teachers, and anyone with an interest in learning more about packet analysis and the importance of identifying the traffic on your network to troubleshoot and identify latency issues. Although most of you have been using Wireshark for many years, I wanted to take a few minutes and explain using NPCAP with Wireshark. When installing Wireshark, the software will make sure that the user has installed WinPCAP, the capture engine for Windows. WinPCAP is an industry standard that has been around for many years. However, it has not had any recent updates, and as a result, it may not perform well on certain versions of Windows 10 and above. To overcome performance issues, users are directed to use NPCAP, as it might perform better. NPCAP comes from the Nmap project and is the packet sniffing library for Windows. Nmap is based on WinPCAP, libpcap, but has improved features for enhanced ability to capture. And I'll scroll down here, and here you can see a little bit more information about NPCAP. Now here is where you can download and install NPCAP. Now, when you're taking a look at this, the Wireshark documentation supports this as well. Now, what I would suggest is that you install NPCAP first and then install Wireshark. But if you're like me and you already have Wireshark installed, then you might have better results if you uninstall Wireshark and WinPCAP and then install NPCAP and then install Wireshark. So I've downloaded and now we can begin that. And then I'm also going to show you at wireshark.org the Windows installer. So you want to get a fresh version of both NPCAP and Wireshark. So I've opened up the installer and we begin by saying I agree. And then as you can see the installation options, there are some other nice features as you can see. Here you can say automatically start the driver at boot time, support loopback traffic, and this is also a nice feature, restrict NPCAP driver access to administrators only, and other features such as support raw 802.11 traffic, and I'll select that, and then I'll begin my install. Now it's installed and we'll finish the installation. Then the next thing I'll do is install Wireshark. Now we get to the part where it asks about packet capture. And as you can see, it says currently installed NPCAP version, and it is already installed. You could install WinPCAP, they are compatible, but I'm going to go on to the next step. This is an option if you want to install USB PCAP, and at this point I'm not going to install it, but you could. Okay, great, now we're ready to start. So throughout this course, we're going to examine pre-captured packets, and mainly from online repositories. Now, a high-level knowledge in networking technology is going to help to clarify some of the concepts discussed in this course. However, if you have a basic understanding of networking terms and concepts, and an interest in the subject, you should be able to follow along with the lessons. When you pick up the phone to make a call, You'll most likely use Voice over IP or VoIP, which is changing the way we communicate. Voice over IP or IP telephony uses the existing internet and network to transfer and route voice traffic in IP packets. In many cases, it's part of a unified communication system. Voice over IP is a group of technologies used to transmit voice and multimedia over an IP network. VoIP can use both proprietary and open standards. Examples include Skype, Google Hangouts, and others. In addition, there's a number of VoIP apps available for tablets, laptops, or phones. VoIP has been in use for over 20 years. However, in the last 10 years, we have seen astonishing growth in voice over IP. The VoIP market is rapidly expanding all over the world in terms of subscribers, growth, and traffic. Consumers and businesses are cutting the cord as more traffic uses VoIP than the traditional public switch telephone network. VoIP is slowly replacing landlines. Studies show that 60% of households in the US and Europe are replacing traditional landlines from the phone company with voice over IP, most likely due to the low cost of bundled services with their ISP. In fact, some states are no longer supporting landlines. Many businesses see the benefits of choosing a VoIP solution. Businesses can lower the cost of local and long distance phone calls by up to 40%. Using voice and web conferencing reduces travel costs, and using VoIP as part of a unified communication solution helps improve productivity, which translates to cost savings for a business. Over half the businesses in the US are using VoIP, with the other half starting to follow. The internet is constantly being optimized to support voice traffic, and products and services are available to combine data and voice networks. Eventually, the internet and the telephone network will be one and the same. Voice over IP offers cost savings, is convenient, and is changing the way we communicate. And that is why we need the tools and knowledge to optimize and improve our networks. Today's world, we use a combination of communication methods, including email, phones, instant messaging, and video conferencing. Communication can be either real time or non real time. Real time communication is synchronous and includes voice, video conferencing, and live chat. During real time communication, the sender and receiver communicate in both directions at the same time. Non real time communication is asynchronous and includes blogs, fax, traditional mail, and email. It's not time sensitive, it's posted and then picked up at another time. Unified communications are tools that rely on a VoIP foundation and combines different forms of communication. Unified Communications provides a framework for consistent user interface across multiple devices and improves business communications. Unified Communications leverages the IP network. We can combine communications across a wide range of platforms, including commercial off-the-shelf tools such as Outlook and Customer Relations Management and mobile apps. Features can include voice, voicemail, fax, chat, email, and video conferencing. At the heart of unified communications is IP telephony, or VoIP. With unified communications, an individual can send a message on one platform and receive the response on another. Unified communications has many benefits, and it improves overall productivity. Unified Communications leverages the IP network, and that is why we must be vigilant in providing proactive monitoring and tuning of our networks. While in a conversation, we must be able to hear and understand what the other party is saying. Voice communication involves analog and digital communication, in that we speak an analog, which is a continuous waveform. In order for the signal to travel over a digital network, we digitize and encode the signal. The range of human hearing is between 20 and 20,000 cycles per second. Testing demonstrates a human can understand speech in the frequency range between 300 and 3300 hertz. This is called the voice band range. Digitization takes an analog signal and approximates how it should sound. The goal is toll quality. A codec converts the analog signal into a digital signal for transmission to remove redundancies and compress the data to enable faster transmission and conserve bandwidth. Codecs typically break down speech into 20 millisecond segments. The lower the bandwidth, the lower the quality. A more complex algorithm will provide better quality for a given bandwidth. There are a number of codecs for packet networks in the G.700 series, as we see in this table. However, the most commonly used is G.711, or pulse code modulation. An algorithm measures how faithful the voice is and assigns a mean opinion score, or MOS. The quality depends on a number of different parameters, including the number of participants on the call, the environment, and the type of equipment. According to industry standards and recommendations, we see that the rating of 3.5 to 4.2 is an acceptable range for voice over IP traffic. And because people like to hear a sound during a call, even if the party is not actively speaking, a voice activity detector detects if there is active speech or not, and inserts comfort or synthetic background noise during periods of silence. Codecs encode or decode a data stream to remove redundancies and improve transmission speeds. The most commonly used codec is G.711, or pulse code modulation. When using voice over IP, most systems have several necessary components that include terminals, applications, codecs, gateways, protocols, and network operations. Terminals are the end devices that interface with the user and include soft phones and computers. A soft phone is a computer that looks like a phone. It allows you to make phone calls using voice over IP. It has a standard phone interface and handset, and many have a digital or video interface for messages and presence information. If using a computer as a terminal, you'll need a headset or a microphone and a speaker. Gateways are devices that convert media streams from one set of communication standards to another by using two main functions: media and signal conversions. Gateways are essential when communicating in a complex network with the public switch telephone network, ISDN, fax machines, and other networks. In order to transport streaming media such as telephony and video teleconference applications over IP networks, multiple protocols are involved to provide setup, communication control, and data transport, and include RTP, Megaco, SIP, and H.323. Codecs encode or decode a data stream to remove redundancies and improve transmission speeds. There are various codecs. Each has specific characteristics such as bit rate and voice quality. WANs, LANs, and the technologies used to access the physical network that IP packets travel are an essential part of voice over IP and unified communications. Routers, switches, and voice gateways carry data, voice, and video between all network devices and applications. The infrastructure must provide high availability, management, quality of service, and network security. A voice over IP system has many different components, all of which play an important role in providing exceptional quality and ensuring an optimal user experience. A protocol is a set of rules that governs how systems communicate with each other. In voice over IP, there are multiple protocols that are involved that provide setup, communication control, and data transport. TCP/IP is the Internet suite that connects devices on the Internet. The suite defines how data is packetized, addressed, transmitted, and routed. Dynamic Host Configuration Protocol supplies network hosts with an IP address and other configuration information, such as a subnet mask and default gateway. Real-Time Transport Protocol transports audio and video. Real-Time Control Protocol carries control information for each RTP session. Real-Time Streaming Protocol establishes and controls multimedia sessions in entertainment and communication systems. Session Initiation Protocol establishes, maintains, and terminates sessions between parties over the Internet, private networks, and cell systems. Skinny Call Control Protocol is a Cisco proprietary signaling protocol used to register endpoints, provide addressing, return call messages, and control phone display. H.323 establishes properties such as audio codecs and logical controls for the media transfer. Demand for multimedia applications is increasing. In order to transmit streaming media successfully, multiple protocols are necessary to provide setup, data transport, and communication control over an IP network. TCP/IP, or the Internet Suite, is a set of protocols that allows us to communicate and exchange data on the network. The suite defines how data is packetized, addressed, transmitted, and routed. TCP/IP is the predominant communication suite and resides at the network and transport layer. Other protocols will ride on top of the TCP/IP suite, such as HTTP, FTP, and SMTP. The network layer deals with routing the packets from the source to its destination. The main players in the network layer are IP and ICMP. IP is responsible for addressing, and it doesn't have any error reporting functions. IP is a connectionless best effort protocol, meaning there's no guarantee it will get to its final destination. ICMP is used along with IP to carry error, routing, and control messages. It does not exchange any data between systems. The transport layer provides data transport, and the key players are TCP and UDP. Transmission Control Protocol is a connection-oriented protocol that provides reliable data transfer by sequencing and acknowledging data. User Datagram Protocol is a connectionless transport layer protocol for data transport and is used for time-sensitive applications such as voice over IP, video conferencing, DHCP, and DNS. On a network, TCP is the more predominant transport layer protocol. TCP is more reliable than UDP because it provides sequencing and acknowledgments. However, we will see that RTP, the protocol that transports audio and video, has a number of different TCP-like fields, such as sequence number, timestamp, source identifier, and control methods that help in the accurate delivery of voice and video. TCP/IP, or the Internet Suite, is a set of protocols that allows us to communicate and exchange data on the network. Dynamic Host Configuration Protocol dynamically assigns IP addresses on a local area network. A Cisco IP phone needs the DHCP server to provide an IP address. Special DHCP option 150 is used to send the Unified Communications Manager's address to the VoIP devices so they can register and receive configuration information. A router can act as the DHCP server for its location, and you'll most likely separate the voice and data networks, so you'll need to use two DHCP pools. I've opened a packet tracer file to show how the commands are used to set up the DHCP pools on a router. Now these commands are pretty straightforward. Let's get into configure your terminal, and we'll start with creating the DHCP pool named voice. Put in the network address, and we'll put in the default router's IP address. And now we'll create a DHCP pool named data. And again, we'll put the default router's IP address, and then we'll put the special option. And then we can exit. Special option 150 is only required on a voice VLAN. However, you'll want to include option 150 on the data VLAN in case you ever use a soft phone on the PCs. So DHCP is also another protocol necessary to carry voice over IP traffic. Real-time transport protocol is a transport protocol for media with real-time characteristics. It's multicast friendly and has many encoding possibilities. Many times, RTP is over UDP, which is a lightweight transport protocol. In order to ensure additional information about the transmission, RTP has a number of different TCP-like fields, such as sequence number, timestamp, and source identifier. So here is an RTP header, and we're going to go through those field values in Wireshark. Now, I'm at this website, which is CloudShark, and I've opened up a packet capture here you can see, and I filtered it on RTP. Now, what we'll do is go to Export, Download File, and what I did was bring it into Wireshark, but you can watch it or take a look at it here. So once you get into Wireshark, and then I filtered it by RTP, now we can just see the RTP traffic. All right, now what I wanted to do was kind of take a look. We'll go to Statistics and Flow Graph and limit it to Display Filter and bring in the flow graph, and here you can see RTP between the two endpoints. Now I'll close this, and now we'll take a closer look at RTP. Now what I'll do is I'll bring up this image of RTP, and we'll just keep it up on top. So down below here you can see RTP, or Real-Time Transport Protocol. Now we'll load this out, and now we can take a closer look at this. Now, when we look up here, you can see a little bit of details that is in brackets, and it says stream setup in frame 1. That is done by Wireshark to keep track of the stream. But now we'll go through those fields. So up here, we'll see the first one that says version. That identifies the version of RTP, and this is version 2. The next one, it's a P, which is for padding. Now, padding is sometimes necessary in any of the headers, as you know, but this may be needed by some encryption algorithms with fixed block sizes for carrying several RTP packets in a lower layer protocol data unit. As you see, there is no padding here. And now we see the extension, and in this case it says false, but if the extension bit is set, the fixed header is followed by one header extension, and in this case there isn't any. Now I'll scroll down a little bit here. Now we're at contributing source. Contributing source identifiers, and this tells us the count, and this is the number of contributing source or the identifiers that follow the fixed header, and in this case there are none. And then down below here we see marker, and I'll just scroll up just a little bit here. The marker bit is used by specific applications that will serve a purpose of its own, and in this case you see that there is a marker bit. Now down below here we see what is our actual payload type. Now this identifies the format, and here you can see G.711, which is pretty common. So this tells us the format or encoding of the RTP payload, and of course that'll determine its interpretation by the receiving application. Now we see the sequence number that is used for beginning that stream, and in this case it's sequence number 1. This is used in order to monitor and reorder packets and also to help detect loss. And this is again where some things do happen across the network. The initial value of the sequence number is random and or unpredictable, and that is of course to protect that stream. Now we'll go down to timestamp. This is used to place the incoming packets in the correct timing order. Now here we see some either synchronizing source or contributing source, and here you can see the synchronizing source identifier. This is when there is any multicast done, and any contributing source identifiers that will identify a source that has contributed to the combined stream. And then you see the payload, which will follow in that. So as you can see, even though, and I'm going to just scroll up here, and there you see your transport layer protocol is UDP. It is UDP, but it has a whole lot of TCP-like fields to help with additional information about the transmission. So real-time transport protocol is a transport protocol for media with real-time characteristics. We know that real-time transport protocol is a protocol for media with real-time characteristics. However, we also need something to report on the status of the streams. Real-time control protocol is a sister protocol to real-time transport protocol that provides control information and statistics for an RTP flow. Now, RTP creates a session for each media stream. Real-time control protocol controls the RTP session by passively gathering statistics and reports information about each session. Real-time control protocol then provides feedback on the quality of the data and characteristics of the stream to the media source and other session participants in order to help localize network problems such as jitter. All sites should use a common type, such as Network Time Protocol or Global Positioning Satellite. This helps support synchronized media delivery and jitter calculations. Now, there are reports that are sent by all participants. Now, this is whether it's a single participant or part of a massive multicast session. To avoid congestion, real-time control protocol ensures bandwidth management by limiting the frequency of reports to only once every 5 seconds. Often, you'll find at least 2 real-time control protocol packets bundled into a single UDP data unit. This will minimize packet processing overhead to the routers. Now, what are the reports? Well, we see a sender report. The sender report is sent periodically by all active senders in a conference. This sender report includes statistics for all RTP packets sent during the interval and uses an absolute timestamp that allows the receiver to synchronize the RTP messages. This helps, and if you kind of think about this as lip sync to keep everything synchronized. The receiver report is sent by all participants that receive RTP packets to report on the quality of service. Within this, you'll also see sometimes source description, and this will send the CNAME or the alias from an existing A record item to session participants if this is available. And then there might be some additional information such as name, email address, telephone number, and address of the owner or controller of the source. At the end of the participation, you'll see a bye message, and this will shut down a stream. It's pretty much a direct announcement that it's leaving the conference. Another report is application specific, and this is a way to design application specific extensions to the real time control protocol. I'm at CloudShark, and here I have a stream that we can take a look at. There is a lot more information in here, as you can see. It is a lot of SIP and also Telnet and other information, but it does give us a good example of real-time control protocol. Now, what I did was I went to export, download the file, and I opened it up in Wireshark, or you can take a look at it right here in CloudShark. So once I opened it, now you can take a look, and there is a lot of other traffic in here. So I can filter by real-time control protocol, and here we could just see the real-time control protocol and the reports that are within it. And as you can see, that they are bundled together generally have 2 or 3 reports in there. Now I'll take this off because what I want to do is go to a specific packet. 529. And here we can actually see 529 is preceded by 528, which has the real-time transport protocol. I want to point out that it is using destination port 8000. Now I'll go right to packet 529, and here we see that this is coming from source port 8001, which is one above. So RTP takes an even port, and real-time control protocol will grab the odd port. So within that, here, we'll just scroll up here, and now you can see the 3 reports, and there is your sender report, and that is periodically sent by all active senders in a conference. And that receiver, the receiver report, that is sent by all participants that receive the RTP packets. And this is to help report on the quality of service. And here we have a source description. And this is information about the source, which you can see, and I'll just show you here a little bit more information about the identifier. And I'll scroll down source description, identifiers within that. So real-time control protocol is a supporting protocol to RTP that passively gathers statistics. Reports are sent by all participants to provide control information and statistics for an RTP flow. Skinny Client Control Protocol is a Cisco proprietary protocol, and it's used to control Cisco IP phones and other Cisco endpoint devices. Skinny is similar to Session Initiation Protocol and H.323, but many feel it's easier to troubleshoot than H.323. We'll see that Skinny starts out and uses port 2000, and then the connection then moves to RTP. Now we're going to take this into Wireshark. Now I have a packet capture that was done in a lab, so here we can see some of the conversation over here on the right hand side. Media path event, off hook, set ringer, set lamp, and other dialogue, so different things that are occurring and the communication that happens that causes the messages that are sent to the call processing software. This then helps the device to take the action that has been indicated. Now, when we take a look at this, we'll see that we know that RTP is being used, but it doesn't quite decode it as RTP. Now let's go to statistics and flow graph. All right, in the beginning, we see some just basic information about some commands that are sent. Now we're going to scroll down here. All right, now what we see there is port 16384, and it's saying it's UDP, but it doesn't know that it's supposed to be RTP. Now I'm going to close this flow graph, and I want to go to take a look at port usage here at speedguide.net. All right, now I just put in port 16384. Now you can see that there are other applications. We do see that RTP is using 16384. So we're pretty confident that that's what it should be. So I'm back in the packet capture, and as you see, it still looks like it's supposed to be UDP. But let's see if the telephony will help us. We'll go into voice over IP calls. Well, we see that, gee, there's something going on. It looks like there should be some activity, and there's some packets. Let's just say play streams, and there's nothing here to play. So we're going to close that, and we'll just close that. Let's help it out. Now, within Wireshark, there is something that we can do called decode as. And we're going to go into the user datagram protocol on the source port, and in this case, we'll say decode as. Now, currently, there's nothing, so we're just going to type RTP. So now we force it to decode as RTP, and now it says it's RTP, but we'll do one more thing just to make sure that it's going to decode as RTP. We'll go into Analyze and go to Enabled Protocols. And down below, we'll search RTP. And here we want to make sure that RTP is over UDP, and we'll say yes. And we're going to say OK. And so we really kind of just forcing it to recognize it as RTP. So now we'll go into telephony and voice over IP calls, and I can see that I know there's some activity. I'll go to play streams, and there's nothing here. Well, we'll do one more thing. We're going to just close this, and in this case, it's already understanding that it is supposed to be RTP, and there's the data, so there's enough to put everything together. We'll go to telephony, and this time we'll go to RTP and RTP streams. Now you can see your two streams, and now let's say analyze. Now we'll go to the analysis, and there we find a lot of the data about the streams, and in this case we can see that in the lower right hand corner we say play streams. And there's our stream. We'll select it and let's play it.
Hello, Mr. Bowler. No ring, but conversation ensues. Okay.
Okay, so now you can see what we had to do was force Wireshark to render it as RTP. So Skinny Client Control Protocol is a Cisco proprietary protocol that controls endpoint devices. When you open it in Wireshark, sometimes Wireshark doesn't decode the stream as RTP, so we have to say decode it as RTP so that the streams can be played back in Wireshark. Today, when you make a call, the communication channel will most likely pass through several different types of networks in order to get to the final destination. As we see in this graphic, a phone call may have to pass from the public switch telephone network through the internet to a corporate voice over IP system. As media travels through networks, gateways are devices that adjust to the different network signaling requirements and convert media streams from one set of communication standards to another. Signaling gateways use two main functions. media, and signaling conversion. Gateways include media gateways, call agents or media gateway controllers, signaling gateways, and translators and mixers. Media gateways convert and packetize voice traffic into an RTP stream. Examples include trunking, such as a SIP trunk that provides an interface between a legacy system and a voice over IP network, and a residential gateway that converts an analog signal to voice over IP. Media Gateway Control Protocol is a master slave protocol that provides a central gateway by handling the signal and session management required during a multimedia session. Megaco is also known as H.248. This performs the same functions as Media Gateway Control Protocol, but is a newer protocol that uses different commands and processes. Megaco can operate with either H.323 or Session Initiation Protocol. Signaling gateways pass voice traffic between dissimilar networks. SIGTRAN or Signaling Transport is a telephony protocol that transports SS7 signals through the Internet. Session Initiation Protocol is an application layer protocol for signaling and control that establishes, maintains, and terminates sessions between parties over the Internet, private networks, and cell systems. H.323 acts as a wrapper for media control and setup and includes H.225, which establishes communications between two hosts, and H.245, which establishes properties such as audio codecs and logical channels for the media transfer. Translators and mixers are middle boxes that are placed in the network that transform the media stream within a session and are sometimes necessary when handling conference sessions or traversing firewalls. Gateways in Voice over IP are necessary to convert media streams and include media and signaling gateways along with translators and mixers. When transmitting multimedia over an IP network, the signal must go through multiple transformations and devices before reaching its final destination. Devices include media gateway controllers. These provide the signaling logic. And media gateways. They provide media logic to convert circuit switched voice traffic to a packet based network. Media Gateway Control Protocol is a master slave protocol that provides a central gateway by handling the signal and session management required during a multimedia session. Megaco is also known as H.248. This performs the same functions as Media Gateway Control Protocol, but it's a newer protocol that uses different commands and processes. Megaco operates either with H.323 or Session Initiation Protocol. Call agents are external control devices in a voice system that have complete control of the gateway and perform all of the administrative tasks. Now here we can see this complex network, and here you can see an interchange between the call agent and the media gateway using either Media Gateway Control Protocol or Megaco. I've opened up Wireshark and I want to show you a couple of the transactions that occur during the session. I'm at this web page here where we can see basic Media Gateway Protocol packages. Now, this is from the RFC 3660, and you can read a little bit more information about this Media Gateway Control Protocol packages. But something that I also found that could help you is understanding Media Gateway Control Protocol interactions with a Cisco Call Manager. Now, what you can do is what I did was scroll down here, and here we can see all the commands. So when we get into the packet capture, we'll see those commands as it's talking with the device. So let's take a look. Now, when I get into this packet capture, what I'll do is show you that there's a lot going on. Now I'll go into statistics and we'll take a look at the flow graph. And as you can see, there's a lot of dialogue, a lot of things that are happening. And what we're really going to focus on is the Media Gateway Control Protocol. So we need to filter by going into Media Gateway Control Protocol, and remember the left-hand side has to be lowercase, and I'll press enter. Now, when you see a little bit of this shows up black and you may be concerned, that might not be an error. Let's take a look. I'm at the Ethernet frame header, and we'll take a look at protocol preferences. Now, as you can see, validate the Ethernet checksum if possible. I'll uncheck that. And as you can see, that's not an error. It most likely occurred because of offloading and it came up incorrect. All right, so now we have that stream coming out, and what I want to do is just focus in on stream index 9. This specific stream is very chatty, so I'm going to right click and say follow the UDP stream. All right, now once I get in here, we can see the various commands. Here we see restart in progress, notification request, and there are other commands. Let me bring that in to PowerPoint to show us a little bit easier those different commands. So for example, in here we see notification request, and this is where the call manager is going to instruct the gateway to watch for special events, such as hooks or different tones. Here we see a notify, and this is where the gateway will inform the Cisco call manager when different events occur. Here we see a restart in progress, and the gateway is going to notify the Cisco call manager that an endpoint or a group of endpoints are taken out or placed back into service. Now, this may have happened for a number of different reasons, and the signal didn't get to the Cisco call manager in some way, so it looks like a restart is in progress. And here we see create connection, and the call manager creates a connection between two endpoints. And then there's some other conversations, as you can see here, on hook transition or flash hook. So there's a lot of dialogue, a lot of commands, and the Media Gateway controllers use Media Gateway Control Protocol, or MEGACO, to control the way the media gateways set up multimedia transmissions. Session Initiation Protocol, or SIP, is an application layer protocol for signaling and control that establishes, maintains, and terminates sessions between parties over the internet, private networks, and cell systems. SIP is the most common signaling protocol used in VoIP today. As a result, manufacturers are incorporating SIP into various products, such as phones, proxies, gateways, and servers. SIP sessions may involve one or more media streams, such as voice and video, and includes video conferencing, IM, gaming, and shared multimedia. For a call to take place, we have to establish, manage, and terminate. SIP sends an invite, which is sent to set up a VoIP call. An invite has a session description that allows participants to agree on the parameters of the call, such as media channels and codecs. In this invite, we see the request line tells me that this is SIP version 2.0 invite, which is sent to sipclio@patra.net, and other information, such as from and the caller's location. Within that invite, there's also the session description protocol. This describes streaming media parameters that perhaps include the format and other attributes so that both parties can agree upon those parameters. SIP messages go through either a proxy or redirect servers. Both will inspect the to field and then contact the location server to resolve the address. The servers include redirect servers that return information to the original sender. The proxy server will forward the message to the endpoint or other server, and a registrar server will record the location of clients and are normally located within the proxy. So now let's step through the process. With the SIP call process, we see first the handshake. This is going to offer a list of supported streams and codecs, and the answer will provide a list of accepted streams and codecs. And then in the conversation, RTP will carry the media directly between the endpoints. At the end of the call, you're going to see a SIP message with a bye in the request line. Now, if you'd like to follow along, go to this website where we can get a sample capture. What we're going to get is Magic Jack in a short test call right here. And then you'll want to open it up in Wireshark. Now, once it's open, we're going to filter. Okay, we'll go up here and we're going to say SIP or RTP. All right, so now we just have those two protocols. And what we can do is go to Statistics and Flow Graph. I'll bring this over and we'll say Limit to Display Filter. So we just have that SIP and then subsequent RTP, the conversation. All right, so now here you can see the invite. And then down below you see RTP. And they're using the codec G.711. We'll scroll all the way down. And there you can see the request. We've said bye, and that means that they want to leave the session. All right, now we'll close this. Now we'll go up to the beginning here where we start with the invite, and here we see session initiation protocol. Now pull this up, and here you see the header, and that again just says where it's coming from. In the request line, there's your invite. And now within the body, though, there's where we see the session description protocol. And you can find other parameters within that explaining what will be supported. I'll bring that up as well. Now, when we can finish up with going to telephony. Now, of course, we could go to VoIP calls, but in this case, let's go to SIP flows. And here you can see the SIP flow, and then down below, play streams. And you'll see the two streams here, and there we could just output to the default output device. And we'll play the streams.
Testing 1, 2, 3.
So that's just a simple example of session initiation protocol, an application layer protocol for signaling and control that establishes, maintains, and terminates sessions between parties. H.323 signaling is an ITU-T recommendation for audio and video communication across an IP network. H.323 acts as a wrapper for media control and includes H.225, H.245, which are both protocols that have a specific role in the call setup process. An H.323 network is made of several components, such as endpoints or terminals, a gateway, and a multi-point control unit. This is used to bridge video conferencing calls, and it includes a multi-point controller for call signaling and a multi-point processor to mix, encode, and switch streams. Then there's the gatekeeper and a back-end service which holds information about terminals, configuration, and billing. The gatekeepers are very useful as they serve as a bridge between the H.323 network and the outside world. The gatekeepers provide address resolution and bandwidth control. An H.225 signal establishes communications between two hosts, which is initiated either using a TCP or UDP connection with an H.225 signal. This contains the registration admission status protocol and negotiates with the gatekeeper and obtains the information of the endpoint it is attempting to contact in order to establish the call. An H.245 control protocol establishes properties such as audio codecs and logical channels for the media transfer. An H.245 protocol includes master-slave determination. Now, this is used to prevent conflicts between two terminals which want to start the process. It makes the decision about which one will be the master and which one will be the slave. Here you can see the H.323 call setup. It begins up above by what you see as Q.931, which has the protocol H.245, and then after that the call then begins the media transfer using RTP. H.323 was one of the first voice over IP protocols that was developed and used by vendors. However, it is a less popular since the development of SIP, but it is still in use. H.323 acts as a wrapper for media control and setup and includes H.225 and H.245, which provides audio codec and logical channels for the media transfer. H.323 acts as a wrapper for media control and setup. H.323 was one of the first VoIP protocols developed and used by vendors. However, it's less popular since the development of SIP, but it is still in use. So I have a H.323 setup and exchange, and I thought maybe you'd like to follow along. So if you'd like to follow along, go to rtpexample.raw and you can extract that, save it as a PCAP next generation. So what I did was I brought it in to Wireshark so we can just see an example of this wrapper and some of the protocols within H.323. Now, when you're in this, we're going to do a couple things in preferences just to make sure that we can reassemble the packets. This probably is already done, but sometimes students will explain that they are unable to get the capture to work or to replay the capture. So let's just go into Edit and Preferences, and then we go into Protocols. And there's a lot of protocols in here, but we're going to just first look for TCP. And we see here it already says to allow the subdissector to reassemble TCP streams and TPKT. And we do see that this is actually going to be reassembled as well. That's good. All right. So those two preferences we'll want to make sure. And when we're going into this, the first thing, and this is where we might see a problem, but we won't, is we want to look at the Q931. And so we're going to start with that. And if we wanted to reference, what I'm going to just show you is a call setup with H.323. So as you can see, the call setup begins first with a connection that is establishing, and then after that you see the H.245, and then you see the media stream with RTP. But the first thing that you see there is Q.931. So when we're in Wireshark, this is your filter Q931. And there you actually can see that that is in the display filter. Now, if we wanted to, you can just see the setup and what is happening here, H.225. There really isn't much going on in here, but if we wanted to, we can go to telephony, and here you can see H.225. This is just one of the telephony statistics. There really isn't anything here, as you can see. In this case, there's a setup, one, and here you have connect, and then call proceeding, and there's one more alerting. So there really isn't anything here, but if you wanted to, you can actually take that and save it as a comma separated value. I'll put it on my desktop and H.225. If you wanted to, say you were benchmarking this type of traffic and you wanted to go back and then do an evaluation, you could. I'm just going to close that, and there really isn't much to see there. Looking at number 4, that fourth packet here, And I'm just going to drop this down here. You see Q931. There's a lot of information in here, and this is using ISDN. So you have bearer information in there. On down below, you see H.225 and user information, message body, and some of the information as far as the setup. There's quite a bit of information in here. I'm just going to drop this down, source information, and who is that M. Gemek, and source information vendor. We'll clear that because I want to type H.245, but we don't need the .H245, and we'll press enter. Now with that, this is where we see that we're doing a little bit more control in that. This is just establishing the properties, audio codecs, logical channels. So you can see terminal capability. This is your master-slave determination. Remember, that's who's going to be the boss, and master-slave determination is used to prevent conflicts between the two terminals and which one is going to be manning the ship and starting the process. And here you see master-slave determination and final acknowledgement. Now, opening the channels and opening the logical channels that take place, and there's one to be sending and one receiving, and the acknowledgement of that. And of course, we see the codec G711. Now, we don't, as I said, have that 245 is the one protocol that we can use, and we can follow the stream, as you see, the TCP stream. We're not going to see anything, but if I wanted to, I could go to flow graph, and we would just limit that to that, and that would limit that stream so that I can see a little bit about what's happening with that stream and that setup taking place. And pretty much follows the format as to how it sets up the channels in H.225. And we'll close that. Now, once the flow is established, we can go in an RTP, and that is your media transfer. Now we can play that codec. Now I'm going to go to telephony and VoIP calls, and then we can go into play the streams. So understand that we are able to play those streams, but it's because the Wireshark is only really capable of doing G711 at this time. But again, you could do this to do a little further investigation of the call quality if you wanted to. So I'm going to close this up. And in general, though, when you're taking a look at normal voice over IP traffic, H.323 is probably one that you're not going to see as often, but you might. And if you are using it, this Wireshark is able to open it, decode it, take a look at the data transfer itself, and help you in some troubleshooting. And keep in mind, H.323 was one of the first VoIP protocols, not used so much, but it is still in use. And you may need to do some troubleshooting, which you can do in Wireshark. When transmitting multimedia over a complex network, as seen in this graphic, it's important that all sites receive the data in the correct format. Translators and mixers are middle boxes that are placed in the network that transform the media stream within a session. They're sometimes necessary when handling conferencing sessions or traversing firewalls. Translators transform RTP media as it passes through a network to better suit the characteristics of the output network. Well, how do we use translators? One way is to provide a bridge between different transport protocols. We can adjust for lower or higher quality bandwidth by converting between media codecs, pass through application layer firewalls, or add or remove encryption. The translator is transparent to participants. They won't even know that the data has been modified. Translators include bridges, transcoders, exploders, and mergers. Bridges are one-to-one and are the simplest kind of translator. A bridge doesn't change the encoding or modify the RTP data. However, it does provide a translation between different transport protocols. Transcoders are one-to-one translators that change the media encoding by decoding compressed data and re-encoding it with a different format. They will usually change the payload type and padding, but all other RTP header fields stay the same. Exploders are one-to-many translators that accept a single packet and generate multiple packets. This is used in multicasts. And mergers are many-to-one translators. When there are duplicate streams, mergers combine multiple streams into one. And sometimes data must pass through networks with lower bandwidth. A mixer is placed in a lower bandwidth area and mixes several streams into a single stream. It re-encodes the data to match the one with lower bandwidth and then forwards the stream across the link. Translators and mixers transform the media stream within a session so that all sites receive data in the correct format. Businesses choose a voice over IP solution to save money on phone calls and because it can integrate within a unified communication system. When implementing a voice over IP solution, it must ensure the same or better quality as a traditional telephone network. Many things can affect voice quality. Issues include latency, which is the delay in packet delivery, jitter, which is delay variation of packet delivery, and packet loss, which is dropped packets. On an internal network, there are a few things that we can proactively do to ensure that the network can handle the voice traffic, such as network bandwidth, equipment selection, and configuring quality of service. Now, studies show that adding more bandwidth is not the answer. A proactive approach is to shape the traffic. Using a packet shaper can improve the performance of time-sensitive applications by throttling back non-essential traffic and prioritizing the voice over IP traffic. For example, this graphic might represent what you'll see on a packet shaper dashboard. Now, today's web pages are interactive by design and will have streaming media playing in the background, which might impact the network. Tune the packet shaper to minimize the impact of bandwidth hogging applications on the network to protect your voice over IP traffic. The quality of equipment is essential. An unmanaged consumer class switch will not be able to prioritize traffic. If a large document hits the device first, it will be delivered and starve out the voice traffic. Ensure that you have the right equipment so that you can manage and prioritize traffic. Voice over IP uses the IP network to deliver voice and multimedia communications. Internet Protocol, or IP, is connectionless and best effort, meaning most of the time it will get there, but there's no guarantee it will get to its final destination. It's like sending a letter using general delivery. Transmitting multimedia needs to be much better than best effort. On an IP network, quality of service makes sure that voice data is prioritized when traveling through the network. When you implement quality of service, real-time traffic is delivered first before everything else, such as Word documents and email. In addition to configuring the devices to monitor and prioritize time-sensitive traffic, if you outsource voice over IP, make sure to identify and discuss quality of service issues on the VoIP contract. Poor phone communication is unacceptable. Manage your bandwidth, ensure proper equipment selection, and configure quality of service to ensure your voice traffic gets the treatment it deserves. Internet Protocol is a connectionless best effort protocol, meaning there's no guarantee it will get to its final destination. Quality of service makes sure that voice data is prioritized when traveling through an IP network. Now, when you implement quality of service, real time traffic is delivered first before everything else, such as Word documents or email. Quality of service is also called type of service, quality of service, or in some cases, differential services. This is a field value in an IP header that marks priority traffic. Now, the concept of priority of service or type of service or quality of service has been around a long time. In fact, here I'm at the original IP RFC 791. And if you look here, there is a field value in IP version 4 that talks about type of service. There are 8 bits or 1 byte that allows you to modify that header to push up the priority. And here you can see some of the priorities and the precedence and what it does for that type of traffic. So when we do look at a header value and we look at what we see as far as class selector values, well, the normal traffic is what's called best effort, and that's the default as 0, and it's just going to do its best it can. And then you see network control, and those are protocols that deal with routing protocols or getting the data through to deal with network issues. Internet Key Exchange, EIGRP, Open Shortest Path First. And here we see signaling, and that is class selector 3, which is a decimal value of 24. So you can see it's pushed up a little bit in the priority. Now I have some examples that I wanted to show you. What I'll do is I'm going to put up on the top here, this is actually the class selector and an image so you can sort of take a look and cross-reference. So as you can see, the default is 0. And in this case, this is just best effort. So what I've done is we are into the IP header. And when we have that IP header there, you can see that what it is doing is providing you with the ability of the differentiated services field. Let me just drop this down here. It is 0. And again, class selector 0, default best effort. Nothing really special there. Well, now we also have one here that I thought was interesting, and that is EIGRP. Enhanced Interior Gateway Protocol is the protocol we use on Cisco routers. And what it does is update the routers, let the other routers know that I'm available, I'm able to provide you with the ability to route traffic. So here you can see that's a class selector 6, and that has to deal with network control. So in our image here, we can see that that has to do with EIGRP, Open Shortest Path First, but that's bumping that priority up pretty high so that it really pushes out that traffic so that the routers are aware that other routers are available to provide routing to their traffic. And here I have Skinny, and this Skinny capture is, of course, a Cisco protocol. And when we take a look at that, that is Cisco is showing you our class selector 3, which is again signaling. And again, that's about normal. We wanted to see that priority at around 24. This was one I thought was interesting. This is Magic Jack. I brought this in and I thought, well, I wonder what that field value is. Oddly enough, what we see for that one is that that is set at 0 or best effort. So we did see a little bit of jitter on that, and that could very well be because the priority wasn't that high. It's just at best effort. So of course that could cause some issues in the data transfer. So as we know, voice over IP has minimal tolerance for packet loss and disruption. When you implement quality of service, real-time traffic is pushed up in priority and delivered faster. Every device that's connected to the internet, such as a web or email server, a VoIP phone, or other end device, has an IP address. Domain Name System, or DNS, maps a host name to an IP address and works like the Internet's phone book. This enables devices to connect with one another. Whenever you place a call to a SIP address, the server will request the address from the DNS server. Once it's resolved, you can make the call. With DNS, there are a number of different types of resource records. These resource records are used to specify a resource type and an IP address to locate the resource. Some commonly seen records are a Type A record. A Type A resource record is used for an IP version 4 address. You might also see a Quad A, which is used for an IP version 6 address. A mail exchange record will redirect mail to a mail server. And the last entry is a service record, which defines available services, such as HTTP, LDAP, and SIP. Similar to the way a mail exchange record is used to send and receive mail, a DNS service record helps connect to a SIP user. In many cases, when a SIP client calls a public SIP address, an IP phone will use a DNS service record to query and determine the IP address and port of the SIP proxy or redirect server. The service record allows administrators to use several servers for a single domain, and then designate some host for primary servers for a server and other backups. Now, this is just the format, as you can see. The standard format begins with an underscore, and then it tells us the protocol type, name, time to live, class, priority weight, port, and target. And here's an example of a service record. Directories are databases that allow a company to centralize all user information and permissions into a central location that is available to many different applications and might be required in order to ensure voice over IP functionality. LDAP, or Lightweight Directory Access Protocol, provides applications with a method to access and modify the information in the directory. Integration between voice applications and an LDAP directory is commonly done in many organizations. In this graphic, we see several components and some of the interactions that can take place within the directory. One common task is to do a lookup of the requested user from an IP phone or other voice and or video application, so that the user can dial the contact directly. Certain Cisco IP phones are equipped with a display screen, so that you can search a user directory. When the user presses the directories button on the phone, the IP phone will send a request to a web server and return the results to the user. Another task is to move and update user information from the corporate directory into the user database of voice and or video applications so the apps have the latest information. End users and administrators will need to be authenticated to provide a single logon functionality so that they can interact with the various corporate applications. In general, directory integration on a corporate network can provide authentication, provisioning, and user lookup, and may be required in order to ensure VoIP functionality. When working with Wireshark, you want to be able to take a look at some of the statistics in the telephony menu choice. So when we're looking at voice over IP calls, Wireshark does a great job of dissecting a number of the common protocols. Those include SIP, H.323, ISDN user part, and this protocol is used in signaling in trunks between telephone exchanges to establish and release calls. And you might not see that often, but it is still available. Megaco, and Unistim, and this is a Nortel proprietary voice over IP protocol. Again, you may or may not see this, but it is supported. Now, when you're looking at the telephone call itself, there's a number of different states it recognizes. Ringing, of course, in call. You might see it canceled, completed, rejected, and sometimes it really just isn't sure what state it's in, and it just comes up as unknown. If you wanted to follow along in a really great capture that you can use and pretty much is used a lot on voice over IP calls, I'm at CloudShark and you can download and open up this packet capture. It's one that I go to because it's a great example. So we can use this to dissect it and evaluate it. And then once I open it up, I renamed it and saved it locally so that we could take a look at this. All right, so when we're in this, as we know that menu choice telephony, and there are a lot of choices, of course, there's only a certain amount that will have to do with what you've captured and what you're doing as far as displaying it and analyzing it. So the one we'll take a look at is voice over IP calls. Now, once you open this, this looks sort of familiar, right? Well, it has a number of different things, this column values that can be modified. If we take a look and we can move this over so you can see all of the columns. And really, what is it telling us? Of course, the start time and what time. Again, this is dependent upon how your time settings are set up in Wireshark. So this is a relative time start according to the packet capture. It's not generally what it actually is. Stop time, and well, there's the initial speaker, and this is the IP source of the packet that initiated the call. Now, this is from, when we take a look at from, this is pretty much what the calling number is. And in this case, this is a SIP call, the from field of the invite. And as you can see, where it's coming from. And well, where's it going to? Of course, this is the to field of the invite. Over here, you see protocol, and that is any of the protocols, of course, the supported protocols, how long it lasted, and then how many packets. And here it lists state. As long as it recognizes the state, it will tell you what it perceives that's the state. And then any comments. Now, once you click on any of those calls, then you can do something with the choices down below. So down below, you can see, in this case, prepare a filter. Now, what we'll do is I'll just move this over here, and I'll show you that if I select that's that first call, and I say prepare a filter, it will run a filter in the background. Now, when I go to that and I've run the filter and I want to show you flow sequence. So I would go to flow sequence and that just tells us that individual call and not much going on, but again, that's just isolating that single call. And what's great is I love the flow graphs because it tells us up on the top, you can see the IP address. You can do a logical drawing to kind of trace if you're doing some troubleshooting. And I'll close that. I'll minimize this, but now if we go back to Wireshark and we can tell that it has been filtered, I can go to statistics and flow graph. And of course, that shows me all the packets, but because the filter's there, limit to display filter, and that will show me what I just saw as we ran that filter. I'll close that. All right, so we'll bring this back up. And another thing is what we can do is down below, we can select any of those calls, and I can say copy. And how I'd like to do it, well, comma separated value, YAML, which is Yank markup language. So either one of those we can do is copy and put it somewhere and do a comparison if we wanted to. As long as I can play a call, I will. I'm just going to close this, and then what we'll do is take out the filter, and then we'll go back into voice over IP calls, and here we'll say play the streams. So once the filter's off, I'm able to see the streams, and as long as I can see them, then we can play them, as long as it's supported. Now, within that, you can see indicators as you see wrong timestamps, inserted silence. And if we want to, as long as that codec is supported, and of course, that's anything in the G711 family, and we'll play that.
¿Por Colota? Por el Atlas, obviamente. Bueno, si
Now I selected stop, and understand sometimes you're not able to do anything as far as start and stop. Sometimes it actually drops the whole thing and shuts down Wireshark. Voice over IP sometimes is tricky in Wireshark. It doesn't mean it's broken, it just means it just needs a minute to regroup, open it back up, and most likely it will play. It does get buggy sometimes, but in most cases it works. And I'm going to close that. And if we take a look again, we can sort those things. So in general, you can see that Wireshark voice over IP calls in the telephony menu gives us a lot of options so that we can evaluate the calls in our capture in order to do an analysis. When working with Wireshark and a voice over IP packet capture, there's a number of different statistics we can do to analyze the traffic flow. If you'd like to follow along, I'm on CloudShark and I got this packet capture where we can go to export, download file, and then open it in Wireshark. So we've used this before and it is just a nice little capture. And as you can see, we do have real-time transport protocol. We see it in there, and let's see if we can get it to come up under the menu choice telephony. Go to telephony and RTP. Wow, okay. We see the streams and stream analysis. Well, what we have to do is help Wireshark by letting Wireshark know that we do have this traffic. So type in the display filter RTP. Now, once you get in there, select one of the streams and then go to telephony and RTP. And we'll start with stream analysis. Now, if we go to stream analysis, I have selected one of the streams. You can see what it did was let's pull this over here. You can see this is a single stream. Now, this is great because it tells me forward, reverse, and ability to graph, but it doesn't have all the streams. So this is a single stream. And again, this is really great, but I'd like to be able to analyze all the streams. So we'll close this. And now we'll go into telephony and RTP streams. All right, now it shows all the streams. And so within that, you can see we can modify the columns if we wanted to, so we can see them all. And we can see the source address, port, destination address, and port synchronizing source, what the payload is, how many packets, what was lost, delta, jitter, mean jitter, and status. So with that, we first of all take a look and we see lost, not too bad, maximum jitter. Well, it looks pretty good. We see a couple that are 7, and that's not too bad. It's still acceptable. Anything under 30 milliseconds is okay. We'd like it, of course, low. But let's just take a look at this first stream now. Make sure that when you select it and it's blue down below, and if you highlight, it says one selected. So there are 5 streams. We want one of those, and now we'll just analyze. So we're going to pull this up. Now, when we go into this, it gives us a little bit of a summary as to what's happening. And with that, we don't have anything reversed, but go to the graph. And within that graph, you can uncheck what you don't want. Really, all I want is just the forward jitter so I can take a look at that. Now over here, we can see the value in milliseconds, and that just goes to a little over 2. And that looks like it's pretty good. Now, if you wanted to, you can play the streams. And in addition, we could save. Now we'll go to save. And in this case, I want to save the graph. And I select save the graph. And in this case, what you should probably do is save it so that you can remember it. And what I'll just do is I'll just put the last numbers in the last octet just to save this 196 to 204. But of course, you'd save it in something a little more reflective. As you can see, we can save it in a number of different formats, and say we wanted to put it as a PNG and say save. And then I can close that. Now, if I want to go open that, I'll open that, and as you can see, there is that PNG file. And we can use that to compare, put it in a report, save it for later. And that's a real nice feature. Now we'll go to this next one here, and here you can see this has a little higher jitter, so let's go to Analyze and take a look at that. And go right to the graph, and again we want to just pull in and take a look at that. And here you can see that that little bit more jitter. And in that case, is that a bad thing? Well, we ultimately like a nice smooth line, but that doesn't always happen just because of the nature of the network today. So that again is helpful. If I want to close that, then you can see that that is also great if I wanted to do a comparison. So those are two that we can just run, and you can examine all of those if you wanted to. But I wanted to just show you another capture which I've worked with before is Magic Jack and short call. So again, go up to the display filter, put RTP, and now let's go to telephony and let's take a look at these streams. Now there are only two, but here you can see that we see the max jitter is a little higher. And I want to analyze that individual stream, take a look at the graph, and really what just we'll focus in on that jitter much higher. And now you see it's set up at 12, and it's pretty consistent. Now, this is where your analysis and seeing how things change on the network as opposed to what exactly it is you're using as far as the software, where on the network you're doing your evaluation, and these things will change. In Wireshark, we can do that analysis by taking a quick look by going to telephony and RTP and take a look and analyze our streams. When working with Wireshark and Voice over IP, we can take a look at SIP statistics and some of the SIP flows. Now I'm in CloudShark and I have a packet capture here. Now within CloudShark, there are some analysis tools. I'll drop this down, and here you can see Voice over IP calls. Now here we can see some of the calls that we have, and we'll tell the protocols and what is happening in that specific conversations. But down below here in the lower left-hand corner, I could go SIP statistics, and it gives me a nice graph as to what's happening as far as the request method and different codes in the reply method and some of the setup times. So that's pretty handy if you wanted to just do a spot check. In addition, taking a look at graphs, I have a filter here, and in CloudShark I can do a quick SIP filter, and you can do a graph if you go current display filter, and that will give you a quick graph of the display filter, and so you can use it to compare and save it to do an analysis later. What I did was I downloaded and opened this up in Wireshark so we can take a closer look and see some of the other types of charts and graphs and statistics we can use in Wireshark. So we went in, and this is going to be telephony, and then down below you can see SIP flows and statistics. Now, SIP statistics just gives me a count of all of the different types of packets and while that conversation is taking place. And as you can see, these different column headers, and I'll scroll down. And here you see that there were 2 ringing, 2 trying, and down below here, register, invite, and acknowledge. So those are the statistics, and I'll close that. Go to telephony and SIP flows. This is to deal with the different SIP flows. Now, as you can see, there are 5. And the column headers are pretty standard, and I'll just move these over so you can see those. And it will tell us the different protocols and what's happening while it's trying to do the setup. Of course, as you go through and you can select each of those, well, what are you looking at? Possible problems. And if there aren't any, you're just taking a look to evaluate those, you can as well. Now, when you're looking at the start time and the stop time, this really has to do with when the packet capture was made. And of course, is it accurate? It really depends. Someone may have filtered it and sent it to you. The time might not be the same, but it's a way to reference what is happening. The start and stop time might just be in relationship to what it was done when it was captured. Down below, you can select time of day, and that actually puts what it perceives to be when this packet capture was made. And this again goes to the statistics of when the packet capture was made and what has been recorded in Wireshark or the packet capture, whatever tool you used. Now, with the problems that you might see, we'll just select any of those here, call setup, and I'll just go to flow sequence. And I'll just move this here so we can take a look at what's nice is it tells me the time, and I can also see the IP address. And we can see any problems. If it's a normal flow of SIP, that's great. Sometimes you might see things such as there's going to be a need for some type of authentication, proxy authentication, and a need for some credentials. In some way, they weren't presented to the proxy, so the call did not go through. So that could be something that you can take a look at as well, and I'll just close that. So all of those you can take a look very easily, taking a look at the flow sequence to see what the type of behavior of that SIP flow. And we also can do this is to select any of those and prepare a filter. And of course, that will put that filter right back up in Wireshark so you just see that specific flow. So you can see those. And in general, again, if you're just looking at this voice over IP traffic and this SIP flow, to just do an investigation and just get familiar with it, see if there's anything unusual. If there is a troubleshooting exercise, you of course would see if there's any authentication problems. Notify isn't always a bad thing. If I see notify, that might simply be a keep alive to keep the session alive, maybe when I'm traversing a NAT device. There's other things, of course, that if the call isn't going through, that's where you really have to take a little closer look. And again, where you do this capture will depend on what you see as well. So in Wireshark with telephony, we know that we have either SIP flows or SIP statistics, which can give us a better idea of the normal traffic flow and if there are any issues we need to investigate. When you take a look at normal traffic, we know that TCP has a natural burstiness to it, and that would include your HTTP normal traffic. We know that TCP has a natural burstiness to it, and that would include your HTTP, email, Facebook, YouTube. We know that that traffic is going to be bursty, and it happens. It's because on the other side, I can put it back in the order it's supposed to be in. Voice and video, generally, we're going to see a constant stream. Now, can we take bursty traffic? Well, here's the thing. You really should test for UDP bursts, and periodically, if you're wondering why are you having so many problems receiving the traffic, let's take a look. If you have this network device, and there's your network device, just any device on the network, and if the traffic is bursty before it enters the network device, that bucket represents the buffer space. In most cases, it's just unable to handle that amount of traffic, and it will then cause an output drop, and you will not get it. So how are we going to check that? Well, I wanted to take you to this website. You can go to the wiki, wireshark.org, and this is the packet capture video multicast. Download it, extract it, and then we can open it up in Wireshark. Now this is just a nice multicast packet capture. And within that, what we'll do is we'll take a look at statistics and UDP multicast streams. So remember in voice and video, we like a nice steady stream so we can see the video. If there's any loss, well, then we're not going to get it. So when we're measuring for burstiness somewhere along the network, we're going to just do a capture. Now in this, you can see that down below, you can set out whatever specs you want to burst measurement, burst alarm threshold, and those would be whatever you would like. Of course, it would depend on your committed information rate, whatever you feel is appropriate for your network according to the length that you have. In this case, let's take a look. In this one here, you see that that burst alarm is 132. I'm going to right click, and now when I right click on that stream, I can either apply as a filter, prepare as a filter, find, colorize, copy, or save as. In this case, I want to apply as a filter, and that will put it up right there. And then we'll just close this. Now, that is the actual stream that I wanted to take a look at. I'm going to select that and copy it. And then in this case, I want to go to statistics and IO graph. And I've already set this up for us so we can take a look at that. And let's pull this down. The IO graphs are pretty darn handy because it can tell us a lot about what's happening. If we go into, this is the one, now as you can tell, we have several, and we're going to uncheck that. This is, I just named it multicast, and in the display filter, if you double click it, then you can just paste that filter that we just put up there. And then I named it multicast. And the color, well, whatever color you like. I thought that that pink was pretty good. We can make it another pink if you like. And I'm going to put that up there. And what is the style? Well, boy, in IO graphs anymore, there's a whole bunch of different styles that we can use. I'll just say with the line. And here is where the interval, I would like to drop this down, and here's why. We'll take this down to 100 milliseconds. And there's where you can actually see that that drop and where the traffic then kind of went back up a little bit more. Again, maybe outside of the range of what you're comfortable with. So here's where we can just do a quick check to see if there's any burstiness and how much burstiness and where is it occurring in order to make some modifications. So when you're on our network, you want to monitor for burstiness, and that's including excessive TCP burstiness and also UDP burstiness. And we could bring that into Wireshark and make some modifications so that we don't have any output drops.